Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to learn how to calculate a Ka from a pH value of a weak acid. Okay, so the weak acid that I have up here is formic acid, okay, and it's going to react with water. It's going to donate its proton to form the hydronium ion, and it's going to leave the formate ion in return. Okay, now the question is going to be, if I had a beaker of 0.10 molar formic acid that has a pH of 2.38, can I calculate the Ka value for that? Okay, and I absolutely can. And all I need to do is use a simple ice chart to get there. So the first thing I'm going to do is enter the initial conditions, okay, which is 0.1 molar of the formic acid. We don't have to worry about water in the equilibrium expression because it's a pure liquid, and it doesn't say anything about formate ions or hydronium ions to begin. However, it does give me the pH, okay? And if it gives me the pH, it gives me one of these equilibrium positions. Specifically, it gives me the equilibrium position of the hydronium ions. Now, I will say this, a lot of students have a hard time figuring out the concentration of hydronium ions from the pH, okay? And that's our big clue, is that we do have the pH. And if you remember, okay, if you do some manipulation of this equation of pH is equal to the negative log of the concentration of hydronium ions, and you rearrange it for the hydronium ions, you end up getting the equation of base 10 to the negative pH. Okay, that's how you calculate the hydronium ions. And I have students forget this all of the time. They have a hard time rearranging the equation to get this. So let's go ahead and put the pH of 2.38 into this problem. So if we go base 10 to the negative 2.38, we get this number of 4.17 times 10 to the negative 3. And that's going to be your concentration of hydronium ions at equilibrium, because that's the only way you would get the pH of 2.38. So if we know that this equilibrium position is 4.17 times 10 to the negative 3, then we know its change increased by that same amount. And as soon as we have the change of one of them, we know the change of all of them. And because this is a 1 to 1 to 1 to 1 ratio, the number stays the same. So if this goes up 4.17 times 10 to the 3, then so does this because of stoichiometry. Okay? And if the products are going up, then the reactants are going down by the same amount because of the 1 to 1 ratio, or because of the stoichiometry. And then when we have this, it's just a little bit of addition and subtraction. We're going to take 0.1 and subtract 4.17 times 10 to the negative 3. And when you do that, you get 0.09583 if you plug this into your calculator. Obviously, this math we can do in our head. If it starts at 0 and goes up by 4.17, then this number is going to be the same value. Okay? And if we have all of our equilibrium positions numerically, then we can calculate the K value, because the K expression is going to be the products over the reactants and all we have to do is plug in the values. So this value here, which ends up being 4.17 times 10 to the negative 3 two times, right? One for this one and one for this one, all over 0.09583, right? And then when we calculate this out, it comes out to be 1.8 times 10 to the negative 4 as our K value. Okay, so once again, in order to calculate a Ka value from pH, you have to use this equation to figure out one of your equilibrium positions. And when you know one of your equilibrium positions, you can fill out the whole chart, okay, and then plug the numbers in to the equilibrium expression in order to get your Ka value. I hope you found this information helpful. If you did, please give it a like and subscribe. And when you add that comment, it really does push this information out to other students that might be interested in learning chemistry.